Здравствуйте, дорогие участники.
Hello, dear participants of the working meeting, the climate change impacts on the natural ecosystems in the Arctic, held within frameworks of the Third Northern Sustainable Development Forum. And we will be moderating. My name is Inakentia Chlopkov. I'm the director of Institute of Biological Problems of Cryo-Lithozoan, and also Professor Trofim Maximov, Doctor of Biological Sciences. You all know him very well. He actually will be the chief moderator today. We have a lot of presentations, so we have maximum 8 minutes per presentation. Those who are present online, please use the button to use translation, the globe icon. You can choose either Russian or English translation. So let's not waste our time, and I give the floor to Teppei Yasunari from the University of Hokkaido. Hello, my name is Teppei Yasunari. It's a pleasure to meet you.
So I'm going to start in English. Let me see. Can you see my slide? Okay. Today I'm going to talk about the wildfire and its air pollution over Siberian region. And before doing that, I'm going to explain briefly myself. I'm working on the field research from a PhD student, and I did develop the GCM and when I was postdoc, and now I'm working for the wildfire and air pollution, and those bunch of the top keywords are the work I have worked. Today, I'm going to introduce you about the Siberian wildfire and its air pollution. And as you know, in the world, many people are facing the premature mortality due to the increased air pollution. And as you can see here, over polar region, so biomass burning is one of the biggest issues for the premature mortality. And this is one example for the Alaskan wildfire. The smoke actually generating the bunch of aerosols in the atmosphere, namely the air pollution. And you remember in this summer in Canada and of course in the Siberian region, so we faced the severe wildfire in this summer too. And recently we found discovered the most of the summer Arctic PM 2.5 during the 2003 and the 2017 were explained by the wildfire aerosol contribution, namely the organic carbons. And we also found the newly identified atmospheric pressure pattern about the circumarctic wave, and which is related to the co-occurrence of a summer heat wave over Europe and wildfire over Siberia and subpolar North America, including Alaska and Canada. So that's why our recent study emphasized the importance of the wildfire study in the future and around the Arctic. And this is one snapshot. The wildfire is not only important for the local region, but also the downwind region, like this example, the severe wildfire in 2014, just
Recording in progress.
highly increased the aerosols, the PM 2.5 from Saha to the Sapporo in Hokkaido within several days. And then that highly increased the PM 2.5 in Hokkaido area. And then Sapporo city just raised the alert for the first time to the citizens for this case. And this is summarized. This was summarized in our recent paper. And if you are interested, then you can take a look at later. And in the future, the climate model projections mentioned that we're going to have more wildfire with more air pollutions if the global warming will be accelerated. So the stronger global warming would generate more pollution to the atmosphere due to the wildfire in the future. And even in the latest IPCC report published in the last month, mentioned that the more fire weathers we're going to have in the future with the medium to high confidence. So that's why this is the first important message for you today. The better projection of wildfire and its air pollution and accurate understanding of current wildfire activity is essential. This is an important message for you. And recently, we have developed a portable PM2.5 measurement system, which is very useful to measure the PM2.5 in your region. And I'm going to explain a little bit. And so the PM2.5 sensor, this is a low-cost sensor, which was developed by the Nagoya University and Panasonic Corporation. And this is a good instrument to measure the PM2.5. And this is a comparison between the station data and the sensor measured data by Nakayama et al. And this is a good relationships, as you can see here. And we recently installed that sensor into the especially developed the installation box, which can control the temperature inside. Always keep the temperature as warm, temperature warm inside, even in the very cold winter in Siberian region. So we just tested this installation box worked under the cold temperature room under the minus 25 degrees Celsius at the Low Temperature Institute in our university. And we also did some comparison with the nearby station data for the one-hourly data. And we did have a great relationship between our measured data and the station data. And also, we installed that installation box. This is the prototype installed in Fairbanks in Alaska, and we will capture the heavily increased the PM 2.5 during the wildfire in Alaska in June and July in 2019. So our system is very useful to capture the PM 2.5, and now it's available commercially in Japan, and it's not so expensive, still very low cost. And so we can install this kind of low cost instrument to many places. So, so this is our future and ongoing the future plans for the measurement of PM 2.5. We already applied the FS Tech for the 8 this system to the Russian region, the 2 for the Khabarovsk and the 6 for the Yakutsk, and already the approved. And we, but under the COVID-19 pandemic, right now, all stopped. We intend to ship our instrument for the Yakutsk, for Yakutsk, maybe in the coming months, and maybe hopefully we can install these PM 2.5 instrument in the coming spring season to measure the PM 2.5 in the coming summer season. And we'd like to provide our data for your research. And I look forward to collaborating with you guys in the futures. And because this sensor is a very low cost and accurate, so we intend to install this sensor in many places in around the Arctic region in the future. And in our future vision is to establish a sustainable atmospheric environmental system for this region. So this is the first step, but the time is limited. I'm going to stop here and maybe just summarize it. So what is important here is that the air pollution from the Siberian wildfire is impacting on the not only the local region, but also the downwind region. And we recently found that the highly increased PM 2.5 in the Arctic during these 15 years were well expanded by summer wildfires coming from Siberia and also Alaska and Canada, and which is related to the newly found the atmospheric pressure pattern, climate pattern. So we named the CAL pattern. And we developed a special installation box for the PM 2.5 measurement for the cold regions. and which is well variated with the observation, and also we could capture the higher increase in wildfire from the Alaskan region. And the future vision is to establish again the sustainable atmospheric environmental system in around the Arctic region. That's it. So thanks, Doug. Спасибо.
Спасибо большое. Так.
Thank you very much.
Thank you.
I would like to also advise our speakers that we slightly changed the list, the succession of speakers, so we are sorry for that. So Trofim Maximov will introduce the next speaker. Hello. The next speaker is, the next presentation is about Scientific Consortium on Global Climate Change, and the floor goes to the first Vice Rector of the National Research Tomsk Institute, Viktor Demin. Hello, dear colleagues. Thank you for this opportunity to speak. Can you hear me well? Soon my presentation will appear. Can you hear me? Thank you. So the name, I think you can all understand. It's the research in the Arctic zone of Russia and in the North Asia. Of course, it's an interdisciplinary research, and it's a networking. This project is interesting, and this project focuses on the catchment basins of Siberian rivers, Lena, Kolyma, Yenisei, Ab, and the shelf of the Arctic Ocean. That's why the project is really global, because the catchment of these rivers is really huge. And the research envisaging and embracing such huge areas, of course, should be significant. That's why we called it Global Changes of the Earth: Climate, Ecology, and Quality of Life. It sounds quite ambitious, but still, it is true. We try to research all the links between all the components of this Arctic system. We understand it as land, as shore, as permafrost, forest, everything. We try to draw up some kind of a pattern or a system, but in fact it's just a very small part of it. But we have to focus on something. So we focus on the main avenue. So the main result is the forecasting of carbon cycle, giving account to all these factors for long-term forecasting of Arctic ecosystem status. We want to get this result in such a way that we could actually offer them and give them to climatologists to create maybe a new climatic model for a more precise and representative forecast. Of course, we need to see what measures of adaptation or prevention there should be. In this field, we also we expect to have some very good results. And here we have the two main stakeholders, Richard Ernst, Mr. Samiletov, Terry Callahan, a very famous Arctic researcher, and we've been working with him for many years. He is our leader in many ways, and also Mr. Pokrovsky. Besides scientific results will have some social results. And you can see them listed here. But the most important is the set of measures to mitigate the damage. We see that the losses and the damage are estimated at very high rate because it's billions of dollars. Here is the architecture of our consortium. We have many components like sea, permafrost, land, and everything. Although these are the main components, and in the center it's to assess and to forecast carbon cycle, and everything plays a part in it. And permafrost is one of the key parts. It's a reason and also a criteria. We have the leading scientists who are focusing on waters, swamps, lands, seas, and of course scientists who are engaged into permafrost. And of course this petal on this flower is quality of life. Another program are carbon polygons. Maybe you know about this program, it's being implemented now. A few points to illustrate the capacity that we have now. The team that is doing the sea shelf, they are starting off to the 51st expedition already, one of the coming days. So they are doing a lot of work. Next slide. We have been developing equipment and solutions. We have some unique solutions. I wanted to present entirely on this device, but we don't have time. It's a possibility to investigate plankton behavior, other sea biota behavior in situ, using digital holography and then transmit it to the ship or to the land, and to really monitor and get information on biodiversity, concentration, locations. It's very important for the ecological part. Also, especially around hazardous facilities like nuclear stations, gas pipes, oil platforms, etc. Another example also has to do with environment. Another solution, it's the cleaning of water. We also flew above Yakutia. I won't comment on this because my colleague Sergei will tell about this more, Sergei Kirpotin, Siberia as a mega installation. So I will go on. So carbon polygon in Tomsk region, I hope all of you know what is it. When you define some area where you detailedly monitor greenhouse gases, you count anthropogenic and natural contributions to these greenhouse gases. You define the reasons and all the rest of the picture, how they are distributed as well. We have here stations in our famous Big Vasyuganska swamp. It's actually is the largest swamp in the world. We have here stations. Some of them are at our university, some of them are of the Atmospheric Institute. And based on these stations, just a few days ago, we won a grant for the project for a carbon polygon. This is how our stations look like. So what is the main thing about these carbon polygons? It's not only monitoring, actually it's trying to find out how to neutralize them, how to recycle them, how to get rid of these carbons. Probably we can cooperate with our colleagues in Yakutia in this domain as well. So that will be it from me for now. Thank you. Thank you. And now the floor goes to Tetsuya Hiyama, the professor from Nagoya University.
Thank you very much, and Dr. Maximov and organizers for giving us opportunity to present our research project. I'm Tetsuya Hiyama from Nagoya University, Japan. And today I would like to report research progresses of PARCS project. Very briefly, the full name of the PARCS is Pan-Arctic Water Carbon Cycles. So due to the Arctic CS decline, precipitation has been increasing with clear interdecadal variations. This is mainly derived from hydroclimate feedback between Arctic Ocean and Eurasian continent or other continent. Consequently, permafrost degradation proceeded, especially after 1980s. This derived change in greenhouse gas budget in the southern polar Arctic region. So our scientific question are, how are atmospheric terrestrial water cycles changing due to Arctic sea ice retreat? How will atmospheric terrestrial water cycle change in the future? How are inundation areas and vegetation conditions affected by the water cycle changes? And how do carbon greenhouse gas budget change? From our project, we expect two outcomes. One is inundation map and vegetation map by the use of water traceable into integrated model, WTIM, and using satellite remote sensing data. And we will derive spatial temporal map of carbon dioxide and methane practice in northeastern Eurasia and Siberia. This is the structure of this project, and in order to attack these scientific questions and to get research outcomes, we structure this project as shown like this figure. The upper part shows the water cycle between Arctic Ocean and Siberia, upper part, and the lower part shows mapping of the inundation map and the vegetation map, and finally greenhouse gases. So we will use several models, numerical model, and machine learning, and satellite remote sensing data. Okay, then I would like to show you our research progress very briefly. So with the collaborative research between IBPC and Japanese Institute, we are conducting flux measurement at two large forests of Spasskaya Pat and LK forest stations. This slide shows long-term changes in the surface fluxes, including carbon. So we have very clear characteristics of NEE, net ecosystem exchange, GPP, gross primary production, RE, ecosystem respiration, and evapotranspiration, ET. Then, if we focus on evapotranspiration, we analyze origin of evapotranspiration. These are our preliminary result. So from these figures, we have very much amount of rainwater originated evapotranspiration water. Around 70% of ET, evapotranspiration water, is originated from the rainwater, and other 30% comes from snow melt water. And ground ice meltwater is quite few contribution to evapotranspiration. So it might contribute to the river water. So we analyzed also origin of river water. This is a hydrograph of Lena River discharge at the mouth of the Lena River. We have very clear double peak. After the snow melt season, the origin of river water comes from snow melt water and rainwater. But in the second peak in autumn and winter, the origin of river comes from soil water and ground ice melt water. This is very clear seasonal variation. And interestingly, ground ice melt water mainly discharges from the upper part of the Lena River basin. Here, this continuous permafrost region around here. So in order to grasp atmospheric water cycle, we modified water vapor tracer model. The right-hand figure shows our modified model result in 1998. Yeah, from this figure, we can deduce very clear percentage of Arctic origin water vapor. This means water vapor comes from evaporated water from the Arctic Ocean, and it comes to the arrive to the Siberia like this. Then these figures shows internal changes in the Arctic origin water vapor. So we focus Western Siberia and Eastern Siberia. And these figures show the time series of Arctic origin water vapor. Especially here in Western Siberia, after 2005, we have a very large contribution from the Arctic Ocean. But in October, November, and December, in Eastern Siberia, we have a large contribution from the Arctic Ocean evaporated water. This is very clear internal variations. So as a result of change in the atmospheric water cycle, inundation area also changed. So finally, we are making inundation map around the Yakutsk region. So we used MORIS data and AMSAT2 data. AMSAT2 is a microwave remote sensing data with machine learning or deep learning. And we got this kind of inundation map daily and 500-meter resolution map. Please see left-hand figure. This is our predicted water covered inundation area. We can see very clear spatial pattern and seasonal variation. So in summary, we did statistical upscaling of ecosystem carbon dioxide practice across tundra and boreal domain. And we did re-evaluation long-term CO2 practice at SPA, SPA and Irrigate Station. And we did trend analysis on the LDVA at SPA and Irrigate by the use of MODIS data. And also we did coupling of isotope tracer model and exercise module. And we analyze origin of evapotranspiration water and river water. And also we did modification of water vapor tracer model. And finally, we made prototype of inundation map by the use of machine learning and data fusion technique using satellite remote sensing data. Okay, these are our future plans, but we don't have sufficient time to mention, so I will skip this slide. But finally, please see this slide. Next year, March, 8th to 11th of March next year, we will have international symposium. So this symposium will be held with online and on-site hybrid system. So please join this symposium. Okay, that's all. Thank you very much.
Спасибо большое. Так,
Thank you very much. And now the floor goes to Sergei Kirpotin, Tomsk State University, please.
приготовиться Максимову.
And the next speaker will be Trofim Maximov. Thank you. It's a great honor to actually get to Yakutia. It's my second time. When I was here for the first time, I'm just telling you while my presentation is being turned on. So first time was January. I didn't see anything. It was too foggy. And right now it's completely other season, and finally I see what Yakutia is like. Although that experience was also very exciting. So here's my presentation. I apologize. I prepared a presentation for Yakutsk, but I have to show the old one. Unfortunately, the PDF presentation, which was updated for Yakutsk, would not open. So here we'll be talking about what Victor already mentioned. It's a principally new outlook on Siberia as a natural collider and so-called mega transect approach or super transect approach. Unfortunately, this presentation was not prepared for this roundtable, so I will select the slides that are relevant for us. So just a couple of words. Dear colleagues, all of us will live in Siberia. That is why very often we don't realize how unique, large, unprecedented it is. Because one Russian poet said, you can see what a thing is only from distance. So when we took French scientists to Teletsky Lake, where there was this road sign, it said Irkutsk and said 1,000 something something. And he asked, what is it? And I said, it's the largest, it's the closest large city. It's not the end of the earth? No, it's not even the middle. So only then we realized how big is Siberia and how unaware of this we are. Because you only have to step aside and look at it from the distance, and then you realize that you live in such a unique and big country. I'm sorry again for this. We all know what is mega science. Primarily, it was used in physics. And for this mega science, engineers, scientists created so-called mega installations. You even can see it on this picture. It's the famous Hadron Collider in Switzerland. Of course, around such installation, there is a lot of cooperation because one country cannot do it. And that's where large consortia come to life. And it's considered to be very prestigious to be a part of such consortium. And we look at Siberia with our new eyes and actually we can view the Western Siberia. It's where we started. So we can view this Western Siberia and Siberia as a whole as a natural collider, because we have all kinds of different zones here. In order to make this structure work as a natural collider, we should establish some kind of infrastructure that would allow us to do so. And indeed, we established so-called mega transects, or so-called mega profile. In Russian it's called profil, from the very south of Western Siberia, from Altai Mountains to the high Arctic. It is very reasonable, and although we focus on Arctic, Arctic is not isolated from all the rest of the continent. Even all the large rivers, like Great Siberian rivers, they start their sources in the south. Like Ob, it starts in Altai and then it goes northwards. It's a large biochemical flow, and the entire system works as one. The same with Yenisei and Lena catchment basins. So this approach to understand environmental processes seems to be very effective, and it's pleasant to know that the same things were done by our colleagues and partners in Yakutia. And Trofim Maximov has the same cluster of stations from south to the north. And in fact, it's also a mega transect approach. So I think that the idea that we will present within this consortium to view Siberia as a natural collider, it will allow us to be more productive, to progress in cooperation and develop this avenue. So that's probably it that I wanted to say. Once again, I'm so sorry for I couldn't turn on the needed presentation, but you've seen the key slides. I think this approach is very promising and future-proof. We are also a part of the largest international T-Mosaic network. It studies land ecosystems, unlike the sea mosaic network. So this mega transect approach was used and is used now by the largest terrestrial program at the Arctic Council. And we are planning to develop this mega transect from west to east by continental gradient. And here we will need partners, and the highest competences and skills that Yakutia has, they can be very useful here. Thank you for your attention. Thank you, and the floor now goes to Trofim Maximov, the Institute of Biological Problems of Cryolithozone.
Медленно грузится. Ну, давайте тогда я начну.
I will start. The climate of the Earth is changing dramatically. And as a result, we see disturbed structures of our environment and the structure of interaction of its parts, atmosphere, biosphere, hydrosphere, and lithosphere. I will tell you about the research that we have been undertaking for over 30 years within 53 international projects with 18 countries of the world. Global warming has to do with increased temperatures observed throughout all seasons, but it also has to do with atmospheric precipitation. And due to climate warming, we see disturbed ecosystems related or resulting from deterioration of vegetation, and also the impact of processes of soil erosion, subsidences, etc. They have a great impact not only on the nature, but the infrastructure as well. So the dominant ecosystems are large forests that grow in permafrost areas. The territory of tundra representatives ecosystems is less than 7 times smaller than large forests. And in these territories, according to our latest data, 1/3 of an entire deposits and reserves of carbon is concentrated. And annually, 1% is consumed in these 2 main biomes. We have different networks of monitoring at different levels all around the globe. And in the northeast of Russia, we have 6 scientific stations. And by the number of these stations, we are the leaders in Russia. It's unprecedented in the world. And I'm talking not only about beautiful equipment that we have, but the number of parameters that we monitor and study. At these stations, we use the same method and use a 4M approach. 1M is monitoring, both horizontal and vertical. 2M is manipulation. We do all kinds of experiments related to global climate warming and abundant precipitation, wildfires. So we water plants, we burn something, that's manipulation. And 3M is modeling, because we have a very big and exclusive database. That's why we should use it for mathematical modeling to forecast future. And 4M is management. It's so-called science diplomacy, when the fundamental science should interact with society and all the stakeholders. The horizontal transect includes 4 world-known, world-famous stations from south to north. This station total length is 1,100 kilometers. The vertical transect includes research starting from space, like atmosphere, then biosphere, hydrosphere, cryolithosphere. We investigate using satellites, using American, Japanese satellites, also aerial monitoring using drones, planes, helicopters. And we measure 5 types of greenhouse gases in this territory. We also use towers and masts. You can see them on pictures. And we also research permafrost. These are our stations. The basic station called Spasskaya Pать, it was launched 69 years ago. This is a medium productivity large forest. A tundra station in Chokordakh, where we study parameters together with European Union, starting from 2003.
Станция Эльгай – это высокопродуктивная.
And Ilgai Station, high productivity large forest. There we do monitoring together with Japanese colleagues starting from 2009, and forest tundra station called Kodak, where we've been working since 2011. We have a lot of good instrumentation. We use different methods, not only for greenhouse gases. We analyze gases, mass spectrometry, and try to calculate and take into account all biochemical components. Except for terrestrial monitoring and investigation, we do some water research in Vilui River and its main tributaries. According to our data, over the last years, concentration of CO2 and greenhouse gases is growing 2 ppm per year. At this slide, you can see comparative data related to mid-productivity large forest. There is large inter-year fluctuations in central Yakutia, in tundra, and in high productivity forest. And when verifying the carbon budget, we need to take into account these fluctuations, because when photosynthesis is increased, you see totally different data. The annual accumulation of tundra forests, it's almost 2-3 times lower than the medium productivity and high productivity forests, respectively. Based on our research, we built schematic models that include all the components of the carbon cycle for forest ecosystems. We also assessed what are the fluxes, the export of carbon and microelements in the Lena River Basin, including its main tributaries, Aldan and Vilui. It shows that from the higher parts of Lena, almost 50% goes to the Arctic Ocean and only 16% from the lower region of the river. The rest of it comes from tributaries. And using our many years data, we assessed Russia's annual budget for main biomes. The annual carbon flux of Russia, it's about billion. And if we include, but if we deduct everything that comes from fossil fuels, etc., it only 160 million tons of carbon per year. Thank you, Mr. Maximov. So the floor goes to Clemens Vilcourt, Magister of University of Amsterdam.
Приготовиться Такигава-сан.
Hi everyone, my name is Clément Delcourt and I'm a PhD student at Vrije Universiteit Amsterdam. And first of all, I would like to thank you for inviting me to contribute to this exciting workshop. This is a great opportunity for me to present you the results of a field campaign we conducted in Yakutia in the summer of 2019, thanks to the support of Dr. Trofim Maximov and the Institute for Biological Problems of Cryolithozone. And I would also like to thank all our collaborators that work with us on this project, which aims to assess fire severity and quantify carbon combustion from fires in large forest ecosystems. And so maybe to start this presentation with a little bit of context. So why did we decide to go in Siberia? So as you may know, climate change is predicted to increase fire disturbance within the circumpolar boreal biome. And this is of global concern, as this high latitude forests store a vast amount of carbon that can be released into the atmosphere as vegetation and soil are combusted. Much of what we know today about emission, fire emission, is based on research carried out in North America. However, ecosystems and fire regimes are strikingly different between the two continents. So recent remote sensing-based studies showed that most fires in Eurasia are surface fires, low-intensity fires that consume less carbon per unit area than the stand replacing fires that are dominant in North America. The few field studies that have been conducted so far in Eurasia tend to confirm this. But as you can see on this map, to our knowledge, there have been no field measurements of fuel consumption from fires in large forest ecosystems. So our campaign aimed to fill parts of this knowledge and data gaps. So that's why we went in the field in 2019 to sample 2 large fire events around Yakutsk. And so here you can see two satellite images of the 2 fire scars we investigated. And so in total, we managed to sample 41 burn plots that we selected within a wide range of fire severity, forest types, and landscape position. And so within these plots, we intended to quantify carbon combustion from 3 main pools. So vegetation, the woody debris on the ground, and organic soils. And as we could not directly measure emission from these pools at the time of the fire, we had to collect a bunch of measurements in burn, but also in unburned plots to reconstruct pre-fire carbon stocks and then estimate carbon loss. So we do not have enough time today to dive into all these measurements, but maybe to give you a quick example. So for the soils, we use the position of these fine lateral roots on the bole of large trees to reconstruct pre-fire soil depth. And so these roots, which are called adventitious roots, grow above the initial root system in response to unfavorable conditions deeper in the soil column. And so we use the position of these roots on the bole of trees to get an estimate of the depth of soils that was consumed by fire. And afterwards, with soil bulk density and carbon content measurements from unburned plots, we were able to estimate the carbon combustion from organic soils. And so here are our estimates. So the average pre-fire and post-fire carbon stocks, as well as the carbon lost per dominant forest types. So we had 3 different forest types, so large dominated, young and dense plots, mixed larch and pine plots, and large dominated but more open and more mature plots. And so in total, the average carbon combustion from fire within our study site was 3.3 kilogram carbon per square meter. And so the majority of the combustion originated from the burnings of organic soils. In average, 80% of the combustion came from the soils. And so if we put these numbers in perspective with previous studies, so this is a figure from a paper published by my supervisor, Dr. Sander Vera-Verbeke, a few months ago. And so we can see that our estimates are much higher than previous estimates made in peatland and Scott pine forest ecosystems. And so we can explain this with for 2 reasons. So first, the ecosystem were different. So the fuel loads in our study sites were much higher than for the Scott pine ecosystem, for example. and also the fire severity was higher in our study area. So we sampled both surface fires, but also stand replacing fires, so very high severity. And so in addition to quantify carbon combustion, it's also critical to better understand what are the drivers of the combustion within our study sites. And so to do so, we looked at the linear relationship between total combustion and a set of variables, including pre-fire stand characteristics and fire weather indices. And so we categorized our variables into bottom-up and top-down drivers. And so here in this table are summarized the coefficient of determination, so the R squared of all this relationship. And we can see that the pre-fire soil organic carbon pool was the most important driver of carbon combustion within our study sites with a R squared of 0.5. And so then we assessed which one of this category was the most important for carbon combustion. So we ran a variance partitioning analysis. And so we found that actually both categories, so both top-down and bottom-up drivers influenced carbon combustion within large forest ecosystem. And so thanks to our field measurements, we were able to assess the magnitude and controls on carbon combustion in large forests growing on continuous permafrost. But there are also ongoing efforts within our team to use remote sensing data to improve our understanding of the role of fires in these ecosystems. And so, for example, in a paper published a few months ago, we evaluated a remote sensing based index, so the difference normalized burn ratio for assessing fire severity using Sentinel-2 imagery. And so we found that this ratio, the DNBR, holds some predictive power for estimating burn death in large dominated plots. So yeah, this work is part of a research program, Fires Pushing Trees North, which is funded by the Dutch Research Council. And yeah, thank you for your attention. And I will be happy to answer any question you may have. Thanks.
And the floor goes to Matsuoka Takigawa, Japan Agency for Marine Earth Science and Technology. Please.
Okay, can you hear me? Okay, can I start? Can you hear me?
Yes.
Okay.
Да, очень хорошо слышно. Можно начинать.
Yes, we can hear you very well.
Okay, so I will start. Yeah, thank you. Thank you, Chairman. Today I'd like to talk about the impact of forest fires on the climate change. So this is a third talk about the Siberian wildfires, and our talk is focusing on black carbon. That is just released from the wildfires. So at first, I'd like to show about the importance of the black carbon and our ARCS project. That is our background research project. And then we briefly show about the result of our observation networks, and then I'd like to talk about the black carbon emission that is estimated using the satellite observations. Then at first, we start about the important about the black carbon aerosols. That is released from the wildfires, and then that is also a part of the short-lived climate pollutant, and also that is a part of the particulate matters PM2.5. So that is a effect on human health that is already mentioned by Tepe Yasunari. So in this talk, at first I show about the importance for the climate change. So last month is a new IPCC assessment report is just published, and then black carbon is shown out here. So that is estimated to enhance the global warming. But the lifetime of black carbon is about 2 weeks. So that is very limited to the south regions, not comparing to the carbon dioxide, CO2. CO2 is very much longer lifetime, so that has a global impact. But black carbon is very limited to the south region, like Siberian wildfire region or something. This is a photograph of black carbon. So that is very small size, but the shape is very complex. And also, forest fire is quite important for the source of black carbon. So the left figure, left panel showing the fraction of the global black carbon emissions. So in global, the natural resources like wildfire or wetlands, that is about roughly 40 to 30% or something. But in the point of view for the Russian black carbon, so this is the right figure showing the Russian black carbon in each emission sectors for domestic energy sectors and transport and agricultural fires, and then forest fire and grass fires, and then gas flaring. So each 4 bars as the result of the 4 different chemical transport models. So as you can see, there is still large discrepancy among the models, but all models showing the importance of the forest fire black carbons. So that is a very large impact for the climate. This is a radiative forcing by the black carbon. So that's why we want to estimate the concentration as how much of the black carbon is released from the wildfire in Siberia regions. So for this problem, there is a Japanese Arctic research project, ARC2, that is just started last year. And the PI for all these projects is Professor Enomoto in NIPR. And then there are 4 strategic goals. So one is this theme 1, advanced observations, and then as a atmospheric theme. This theme is led by Professor Koike in University of Tokyo. And under this program, we are conducting model simulation and also ground-based observations in Alaska and Siberia, and also SIPPON observations. So this is the outline of our black carbon observation networks. So our observation for BC in Siberia is conducted at the Spasskaya pad. So with the great help of Toriformi-san, and also we also conducting black carbon observation at Poker Flats in Alaska. And this blue color showing our research vessel, blue color showing our research vessel Mirai. So this is not a icebreaker. So this is the observation cruise period is limited to the summer or autumn for this course. Yet this year, this mirror is locating around here. Yep. So, so this is an example of the column amount black carbon in year 2016. So red color showing the anthropogenic black carbon, and then blue color showing the forest fire black carbon. And this is the Spaskai path, and this is Alaska Orca flat. So, so, then this is the Mirai. So Mirai is on the Bering Sea. On this year, we succeed to capture the biomass burning around the Baikal Lake. So the rough distance is about 3,000 kilometers, but still there is a strong signal of black carbon, high black carbon concentration up here. And then this is a brief observational concentration at the Spaskai part. So each circle is showing the observational concentrations, and each color is showing the different years. So in summertime, there is some biomass burning impacts. And so like this kind of seasonal variation can be seen. And also we compare with ACC chemical models international comparison projects results. So each line shows different models output. So there is a very large discrepancy among the models. So the vertical bar is log scale. So that means there is more than 10 times larger in these two models. So the thick black line showing the Japanese model. So this one showing very good agreement with the observations. And also this is a satellite data-driven black carbon emissions from year 2014 to year 2019 around the Yakutsk, these regions. So there are several inventories, 1, 2, 3, 4, 5, 6, 7. There are 7 global biomass burning inventories, but still there is large discrepancy among the models. That is because of the difference of the emission factors and the treatment of undercover vegetation and peat fire or something like that. And this is the annual black carbon emission around Yakutsk, average for these years. So there are very large discrepancy among the emission inventories. That is showing the ground truth is quite strongly needed for the precise estimation. So this is one of the possible cause of discrepancy among the inventories. So right panel is showing the how much of the burning is hidden by the cloud or haze. So darker blue showing the very dense clouds are covered all over the target regions. So as you can see, Siberia region is a little bit darker. So that's showing the clouds is hiding in the hotspots. So this is the zoom images around the Yakutsk. So also, as you can see in the global map, Yakutsk is also heavily covered by clouds. So that's showing the from satellite there is some difficulty for the detecting of the hotspots. So this is a general summary for my talk. So forest fire is quite important source for black carbon. So it might affect for the climate and public health in the pan-Arctic regions, not only limited in Siberia regions. And also, we have succeeded conducting ground-based observation at Spaskai Park. So that is very useful for the validation for the chemical transport model and local emissions like forest fire. So reliable and continuous measurement is a basis for the elucidating the chemical and climatical impact of Siberian forest fire. So we are very happy to conducting this kind of research and hope to continue for long years. Thank you very much.
Спасибо, Такигава-сан. Сейчас я бы хотел слово представить для выступления Михаилу Стешову.
Now I would like to give the floor to Mikhail Stishov. Are you here, Mikhail? WWF Russia, please.
Mikhail Stichov. WWF, please. My dear colleagues, I have more of information message to you. We're a division of WWF Russia. For the last several years, we implement this project with a long name, preservation of biodiversity of animals and biodiversity in the northern Russia, a little long. We'll keep going for the next following years. As you know, we are working on areas that are protected areas. And 3 models of project regions are Yamal, Taimyr, Chukotka, and we touch other neighboring regions in some circumstances as well, including Yakutia and others. One of the divisions is organization of system for environmental monitoring that is needed on protected areas to track any changes happening to flora and fauna. Arctic nature is among first being damaged by risks of climate change, transformation of nature complexes, including guarded species. We really need to keep track of condition. And this monitoring, effective monitoring, is not possible without full understanding of how everything works.
Общих для целых провинций и секторов нашей Арктики. Ну и, собственно говоря, в этом разделе были, так сказать, поставлены такие вопросы, что нам надо было выяснить, какие компоненты природной среды в первую очередь необходимо изучать, чтобы иметь более-менее полноценные представления о происходящих изменениях, какими показателями можно оперировать при проектировании мониторинга наблюдаемых изменений, как и когда собирать те или иные данные, выяснить, едина ли система этих показателей для разных секторов Арктики и природно-климатических, так сказать, провинций. Ну и как должна осуществляться интерпретация данных, так, чтобы она еще и была доступна как научным организациям, профильным ведомствам,
and including with indigenous people's lives that connect every aspect of living in the Arctic. We conduct space images, and it allows to involve analysis of investigated condition of protected areas. This includes protected areas of federal scale in Chukotka, in Taimyr, other areas as well. So main activity was aimed at producing multiple space photo shoots of protected areas. We analyzed anomalies in redistribution of snow cover in the winter. Similar activity was conducted to condition of ice coverage in the winter. This work is going on right now. Continues in Wrangel Island, in Yamal. So we tried to solve 3 blocks of goals to track dynamics of climate change factors on ice in seas, to track changes in sea shores, and analysis of dynamics of tundra condition. Some of the things were resulted in publications, reports. Speaking about sea ice, in all sectors, we track increasing or speed of melting of ice. Directions for ice moving in the seas changes as well. They move in different trajectories. This creates problems for habitat of sea animals. Because of these anomalies, it changes habitat routines of Arctic animals, including polar bears, who originally use moving ice, floating ice for survival. We also track increase of black ice cover. All this leads to reduction of strength of ice to sand. So we can see that change in habitat conditions is very dramatic, and it's becoming more extreme with time. Talking about shore areas, on open shores, we tracked erosion of soil, more dynamic changes are visible on long peninsulas. This also affects to animals inhabiting seashores in the Arctic. Second important thing is dramatic expansion of the greens growing on the shores. These are especially visible from the Arctic, from the Atlantic side of Arctic. Talking about tundra ecosystems, very active exogenous processes, especially important. Yes, I'm almost finished. Because of changes in tundra ecosystem, original flora and fauna is being replaced by more moisture-loving species. This creates a change in as a whole of a whole process. This is a part of a whole changing process. We developed methodics for monitoring the areas of tracking dynamics of change. And because of this, we came up to several important hypotheses. So here I need to stop. We produce methodics, and we hope in a year or two we will study the system better. Thank you very much, Mikhail. If you had a presentation, that would be great. I'm sorry, I don't have a presentation. I kind of didn't have time. So the floor goes to Petrova Elena. And his report goes now.
Please, Елена Троева, Institute of Biological Problems. I'm sorry, I will have to speak Russian, and I will ask the interpreters to translate. The report is called Climatic Modeling of Distribution of Hemp in Yakutia. Although it's just a example of climatic issues in Russia, but we just want to show that everything is connected. The object of our research is quite controversial, and we see all kinds of reaction when we say hemp, but it's a very good problem, and we focus on it. And in the 90s, we had many abandoned fields where they started planting hemp. And the hemp sometimes accompanied the grains, seeds that were used that were not very high quality. So we had to fight with it, but any fight should be scientifically substantiated. And we study the ecology and biology of hemp in cryolitha zone. We also develop legal regulations and trying to look for methods of controlling it. And today we will be talking about the habitat. The main places where hemp growth is the arable lands, farms, private gardens, and in this year we published our results. And we go back to our research. How we figured out the habitat of hemp. We based on the fact that any plant chooses the most comfortable conditions in ecosystem. Temperature, humidity, moisture, soils. That's what our model is based on. When we were selecting the ranges of ecological and climatic factors based on which we built our model. And hemp is a seasonal plant. Temperatures of June and July play a big role when hemp grows the most. And of course, temperatures above 10 degrees. Which is very important for any plant. We need to construct this model, why do we need this potential habitat? Because Yakutia is very large. We cannot visit all corners of it, including even the most populated central Yakutia, because we still don't have roads even there. We were not able to visit all the communities. The potential habitat is exactly the measure that would allow us to plan some preventive actions in any place where it possibly might occur, which is better than fighting the actually growing already existing plant. Because time-wise and financially, it's very demanding.
Собственно говоря, потенциальный ареал.
The potential habitat of hemp, we already have it. It was created in the All Russian Plant Institute when they created their maps. So if we look at this habitat in Yakutia, we see only the southwestern part of it. And the central part, where the majority of hemp or cannabis grows, it's not included here. That's why we had to build our own map and of the hemp habitat. This is the model that we have built. Based on algebra, we took the ranges of values from the previous slide. These are the places where we have the best conditions are present. Here we have central Yakutia covered, where we actually found the plant, but also there are some spots in the northeast of Yakutia, in Yana, Indigirka, Kolyma rivers. It coincides with the spots of steppe vegetation. These are regions where the seed of cannabis comes from somewhere. A plant can start thriving there. It's interesting that from 1929 data, there was cannabis found in Srednyekolymsk. We could not confirm it, but theoretically it appears to be possible. Of course, our model is not perfect. Here we don't have Kola Peninsula, where cannabis is growing. We also don't see Kamchatka, Magadan, but we work with Yakutia. That's why our model works for Yakutia pretty well. This is the same model, overlapped by the road network and railroad network. And this orange and brown lined areas are the agricultural regions of Russia, where we get all the seeds and grains and cereals imported from. If we look at our republic, arable regions and lands also coincide very well with our model. Red polygons are the places where we exactly found growing cannabis. If we talk about climate change and possible habitat change, climate change is real, and we used here a slide of WWF in Russia, the IPCC good and bad scenarios on temperature change, the high latitudes will be the most affected by it. The same with precipitation. Maybe it won't change that much, but the northern part of hemisphere, especially Arctic regions, will be affected the most. Roshydromet, Meteorological Agency of Russia, they have a map where we can see the changing temperatures and precipitations in different regions. Here we have RCP 4 and 5 scenario, which is the medium scenario. And we have 3 periods. For the short term, the temperature might raise 1.6 degrees in Yakutia, which is quite considerable, significant for environmental conditions. The same with precipitation. 0.1 millimeters per day. It's not that much, but still it's a change. And we will use also the worst scenario and the medium scenario for our modeling of cannabis habitat. These are our expected borders, limits of where cannabis can proliferate, almost to the Arctic Circle, according to our assessment. And these isolated spots will maybe combine, and maybe it won't go that far south. But we will continue building our model and we'll see how right we were. And that's it from me. Thank you. Thank you. Next speaker is Afanasy Pesterev from Northeastern Federal University. And the next one is Andrei Spiridanov.
Афанасий, мы вас слушаем.
Let's see, we're listening. Good evening, everyone. Today we will discuss climate change that happens, and we'll try to prognose possible transformation of these factors. And in accordance to this, how can we produce some sort of solutions for these challenges? But first, we will see what problems we have and that we observe right now. Today, our industries emit about 40 billion tons of carbon emissions. So this raises temperature by 1.1 degrees Celsius. And in these conditions, to prognose something in 20 years' time, we can expect another 1.5 degree Celsius raise of temperature. So we see how mid-year temperature rises on Earth. We can already see that in maybe more southern countries like India. We see very high and humid climate to come, and the temperature can even rise even more. And this can create conditions that will make living even harder, maybe even impossible to live. So since temperature is rising, and on the graph shows how temperature rises in the polar circle. And this rising of temperature, for example, this creates risks on Greenland that can completely melt, that can thaw. So this can cause climate change in Europe that can involve anomaly in summer heat, untypical storms, floods. Floods already happened this year, last year, with huge financial damage. In Siberia, you all know the forest fires were very great. In 2015, we signed the Paris Agreement, where all countries agreed to 2050. They must reach 2050 with zero carbon footprint. But currently, European Union made this agreement legal. So they agreed they will reduce emissions to zero by 2050. They trying to reach this by reducing emissions, by introducing carbon tax, by banning vehicles with internal combustion engines, higher taxes for transportation, sea transports. Here we see that Arctic is thawing very quickly. So every year the Arctic thaws more and more. This graph shows expansion of carbon dioxide level. Right now we all know that the biggest emitters on Earth are two world leaders, United States and China. They emit about 50% of all carbon gases. And we know that under Trump presidency, United States pulled out of Paris Agreement, but President Biden returned. So President Biden aims to achieve a 50% of rating of vehicles sold in the United States to have electric engines by 2030. And the United States budget has $3.5 billion for climate change, for global warming issues. China has approximately the same results. And but Chinese emissions are, the biggest share comes from burning coal for power stations. So China swaps for nuclear power stations and for wind turbines. Also, they all search for newer forms for reducing the carbon footprint. For example, hybrid power plants to power, for example, water supply stations. Russia also follows the trend, doing its part. Currently, there were no plans of reducing carbon emissions. Still, Russia started its program of decarbonization, and the program expenditure for this is about 30 billion rubles for climate change issues. This was sounded by Viktoria Gabusheva, and Russian Ministry of Economic Development developed a strategy that will reach higher carbon absorption. So this can lead to further moving to greener technologies, but this will cause rising of prices to services and cost of goods. For example, electric vehicles, creation of newer technologies, this will all be very pricey. Also, so-called carbon taxes will affect economic development. For example, European Union countries already have it, and import of goods from European Union also is getting more expensive. So we need to strengthen our joint effort. So I'd like to focus on developing green areas in urban areas, especially in industrial cities, as this can help tackling the issue. Thank you very much. And the floor goes to Russian Forest Protection Center in Buryatia. Please.
Добрый вечер, уважаемые коллеги. Федеральное бюджетное учреждение «Русозащита» в лице Центра защиты леса Республики Бурятия ведет ГЛПМ, то есть государственный лесополитический мониторинг Республики Саха-Якутия с 2012 года. Ранее работы эти проводились методом лесополитических экспедиций. В результате государственного лесополитического мониторинга производится оценка влияния различных неблагоприятных факторов на лесные экосистемы, в том числе насекомых вредителей, и планирование работ по снижению последствий их воздействия. По архивным данным и данным филиала
Data of Russian Academy of Science in Yakutia and by science expeditions. And Siberian, constant growth of silkworms is tracked in western areas of Yakutia, in Yakutsk, in Aldan River. In Vilui wasn't detected. Expansion of silkworm number in all areas on the other bank of River Lena is high. The biggest notable appearance of silkworms was tracked in 1999. In the next 2000 year, the same happened to Khangalasky Rayon in Yakutsk. We tracked very high amount covered with silkworm. Damage from their appearance on some areas could reach 20 to 100% of damage done by silkworm. After reaching peaks of amount of silkworm, the amount started to reduce slowly. Normally, silkworm goes with goes for expansion inhabiting berry covered forests, cranberry forests. On mixed types of forests, and peak for expansion of number of silkworm peaks in July. In years of peaking amounts of silkworm butterflies can reach higher amounts as they can lay eggs. One species can lay up to 30 eggs, so it's highly resilient. So main reasons for expansion of number of silkworm are droughts, reducing winter, higher temperatures in summer, which is all caused by climate change. High amount of rain in summer forces silkworm butterflies to spread more around areas. So this threatens nature even more, and if nature is not protected for at least 1, 2, 3 years with high number of silkworms around, the damage is extremely high.
Для анализа вспышек массового размножения шелкопряда от климатических условий нужно учитывать такие факторы, как засушливость климата, повышение условий увлажнения в период лета и мощность снежного покрова. Влияние изменений климата явилось первой предпосылкой к возникновению вспышки массового размножения сибирских шелкопрядов в период с 91 по 95 года. Эти годы засухи оказались благоприятными для шелкопряда, и они обусловили постепенное нарастание его численности. Дальнейшее его нарастание шелкопряда было обусловлено резким снижением мощности снежного покрова. Это привело к гибели перезимовывающих в поверхностных слоях насекомых фотомофагов, естественных врагов шелкопряда. Исчезновение их способствовало интенсивному размножению шелкопряда и резкому увеличению численности. Последующий в 2022 годах засушливый период позволил бабочкам шелкопряда поколения 97-99 годов широко распространиться на территории и стал основой для его массового размножения. Высокая численность наблюдалась в течение 3 лет. Одновременно с интенсивным ростом численности происходило постепенное нарастание численности насекомых энтомофагов, и уже к 2000 году их численность достигла максимума. Такому нарастанию численности данных насекомых способствовало выпадение довольно обильных осадков в зимнее время. Таким образом, можно говорить о решающей роли климатического фактора в возникновении вспышек массового размножения сибирского шелкопряда. Аналогичная ситуация наблюдалась в 2017-2019 годах, установившие критические показатели.
Same situation happened in 2017. Nature conditions was hot and dry, so this created a dangerous conditions for further expansion of silkworm number, especially in around vicinity of Yakutsk, Khangalassk, along Leona River, in Gorny, Ulus, in Nancy, and created migration areas that reach up to 350 hectares. We established that population, that yearly population has expanded. In 2021, we tracked routes and studied the routes, so in future we can know earlier further migration routes for silkworm. Thank you very much. So now word goes to Pavel Ktitorov. Next is Michael Chirosov.
Так, Павел, что-то звука нету у тебя. Включи эту микрофон. У тебя показывает, что отключен он.
Да, прошу прощения. Сейчас обратно.
Вот теперь слышно. Ага, пожалуйста, Павел.
Да, добрый день,
Hello,
коллеги.
please. Dear colleagues, today you heard about climate change and especially about hemp and about silkworm. And I will talk about population of sparrow birds in Chukotka as a result of change in tundra conditions.
Так, появилась презентация.
Да. Ну, как вы знаете, большинство...
As you know, majority of biologists in the Arctic normally study larger amounts, larger types of birds. Majority of research are dedicated to them, and as a result, smaller kinds of birds, as shrub-dwelling species, are not noticed, and change in their populations are not visible often. They're registered, but they are not treated seriously. And our first pilot work in our research that we conducted in our stationary in Pevek, and we compared it to types of birds that appeared there for the last 10 years. Since 2003, it's more than 10 years. And compared it to data of our colleagues acquired in 1970s, 80s. And changes happened in this area. For example, lampland bunting. I'm showing this on the screen. The number has reduced. Redwing, as well as fieldfare, dusky warbler, Siberian ruby-throat. So we made this first article about this result. This was surprising. At first, we thought that these changes accorded to change of space, a change in trees and biomass of grasses. On that area that we researched, nothing changed actually. On a larger scale, that's the result, part of results of an international group that does reports on climate change in the Arctic. In yearly report on climate change, for example, this area on Chan area of research, biomass of greenery is actually quite high. We could visit other stations, especially borders of taiga and tundra, where we studied tundra birds, for example, wagtail, chiefhalf. Then we compared literature data to our data as areas for inhabitation of these birds changes. And biggest change happens to Turdus Polaris. It moved more to northeast through that time.
Целый ряд исследователей долгое время, если почитать литературу 70-х годов, то область
and it's surprising because moving off in inhabiting areas to the northeast is not connected to change of temperature. This is not only about land birds, also kinds close to small land bird types. Far migrating species in Chukotka that 30 years ago they thought birds like this could not be seen in these areas, could not even reach these areas. Now they're there. We were sure when we started that the change was connected to change of inhabitation conditions were connected to changing trees and plants. But this also included non-forest birds from other types of habitats.
И, в общем-то, известно уже, по крайней мере,
for example, in Alaska, there is a kind studied more than 100 years. It's a green-cheeked thrush. It's sort of similar to North American counterpart of NA sparrow. Quite recently, there was a publication dedicated to other issues about why birds migrate. You can see these orange glimpse on Yakutia and in Russian, comparing their models, the amount of migrating bird species are far behind from other models. So this process is a process of occupying free niches by these birds. We've got an unexpected result, for example, where we expected to see new species about 300 kilometers east of National Park. And we were surprised that we've seen that fauna has not changed. And it was still since like 1930s. And we cannot really tell that climate doesn't change or anything. Warming in different areas in here is very notable. But still, there is some kind of a barrier or a wall maybe it creates obstacles for migrating birds. So this is something that we need to research a little more. So thank you very much for your attention. So not only birds occupy Chukotka, but also brown bears too. Thank you very much, Pavel. And the floor goes to the last speaker.
Институт биологических проблем, клетозоны, саран. Михаил, буквально 5 минут нашего времени уже все потратили.
Пожалуйста, презентацию. Ну,
Is your presentation?
специалисты по геоботанике тоже присутствуют, они знают, что
Specialists on botanics are here. They know that use of space photographs
сложная такая процедура.
is very complicated procedure.
Так, придется быстро. Ну, контекст то, что это мы взяли.
Context here of you picking mountain territories is it's quite complicated.
И взяли территорию, вот она у нас в Якутии, это на границе Ледобатантайского и Жиганского районов. Довольно большая территория, Московская область, вся тут помещается. Идем дальше.
Moving on. And as a whole, this typical structure you're able to see it very closely. These are names of mountain chains, so you can see it more clear. And for the 2 years, we developed this methodology of using space pictures from different time periods. We used approach of RDVI, different algorithms, and we developed this program that allows to use the artificial intelligence here too. There's another technology called Google Earth Engine. It's a good platform, everyone uses it. This model allows to use these pictures and process them. We developed methodics for research from Landsat Sentinel satellites that everyone also knows. On this territory, we have about 3,000 pictures taken and divided by time of taking picture. We haven't counted what happened 20 years ago and now yet. And this led to us taking a relief approach and approaches to fleeted sensor. Moving on. And after that we worked through this scheme, especially important was of us using pictures of different dimension and our preferred scale was 1 to 100,000. It's quite convenient. And we created 387 training data and 550 validation points. So there we could extrapolate and to further use machine education for research of these territories. And when we compared map of plants compared it to a landscape map, we had big differences. We thought this was a mountain tundra area mostly, but we realized that it's at best maybe 20%. So we find out because of this. And that's slightly another way. You can see percentages. For example, 20% is mountain tundra ratios. These are mapping geobotanical divisions. We can use approach of Grand Catchment. We work like this so far, and the last thing that we did, the lighter areas, we compared it to earlier years, 20 years ago, and the green part is the stable core. So we can use these technologies to divide these huge space shots into smaller ones. We cannot count all of them yet, but this is very good technology to use. So as a result, we can say that the system is very universal It has its topology, allows for large scales. If you have interest, we may cooperate, and those are preliminary results that we have right now. And we're glad that we have specialists of different fields and we can work together. We have an article about this, but we need to get published first. Thank you. I try to be very brief. Ready to cooperation. Thank you very much. So this concludes our meeting. And before I give the final word to Maxim Trofimov, and I'd like all participants to say thank you to those organizing. I'd like to invite the secretariat of our forum, Susanna Igorova. Because of these young people, today we had our meeting and all in right time. Let's thank them. And to conclude, I give floor to Maxim Trofimov. Dear friends, thank you very much for your active participation in our meeting. It is very obvious that this is a period where we need to work on global warming, using science to hold transdisciplinary research, to establish roles of Siberian ecosystem as a part of global climate change. And these aspects are important on research that's conducted by international projects. And now we support an initiative from Tomsk State University as well. They will promote and help us in our efforts and our research. Scientists of fundamental sciences, but we also need to go with science diplomacy. We need to communicate with community. We need to touch interesting sides to decision makers, so they finally understand that this problem is real, this problem exists. And if we don't act now, this can be catastrophic for all us living on this planet. Science educational part of the effort is extremely important as well. Creation of international education centers with employing Russian science. It's important for perspectives and further development of our beloved science. Thank you very much for participation. All the success to you and new achievements. Thank you very much. I'd like to add that we will need a resolution of our working group meeting. If you have anything to add, please send it to the email that we have in the chat. So I offer cooperation to everyone interested. You see, Yakutia is a unique region, as you could see. Even just by looking at that 30% of Yakutian space are protected areas thanks to WWF, and only small percentages are taken by mining industries. And all the processes are mostly natural, especially even land fires, still natural. Everything burned even before. And reasons for fires, not just human factor. You see, human factor only is a percentage, is not a full, not fully what happened. So we constantly open to cooperation, and we believe that on our territory, we will get fundamental or practical results that will tackle climate change. We will see you in the future. Bye-bye.